Okay. So static generally means not moving, but we need to be more specific. And the two objects where the friction exists, they're not sliding against each other. So, for example, if I push on this table right here, it's not sliding, so there's static friction involved. Not to imply it's not moving, because movement is always relative to something. I mean, anyone who's walking around, this thing is moving relative to them. So it's a matter of what is it doing relative to the object it is touching. So objects in contact are not moving relative to each other with respect to each other. And then kinetic, they are moving with respect to each other, or there is sliding going on. Now, when dealing with friction, in screen there. Shift that over. Probably a little bit blurry, but is this in screen on screen?
No,
It is not.
it's got your fingertip, but so you're almost there.
All right, so if I push on this, right now I'm pushing on it. If this were a frictionless surface, what would this mass do? Right, but it's not moving, so it's not sliding, therefore there's got to be something keeping it in place, and that would be the static friction. Now I push a little bit harder, and you can't necessarily see that I'm pushing harder, but I can feel it in my fingers that if I'm pushing harder on this, it's going to be pushing harder on my fingers, and so that's what I'm feeling. I push harder on it, and it's still not sliding, so the static friction is still there. Now when I'm not pushing much, absolutely spectacular drawing there. So if I pull with 1 Newton, push with 1 Newton of force, how much friction force is there to keep it in place? Assuming that we're still in the static situation.
Not 1/8 newtons. Or is that-
More than 1 newton.
I heard of more than. If I had more than 1 Newton there, and by the way, yes, you're correct. If I have 1 Newton pushing this way and I have more than 1 Newton that way, I have an unbalanced force. And that would have the thing accelerating backwards. So, how much friction is there?
1.
Yes. It is just enough to keep it in place. If I push with 2 Newtons of force, and it's still not sliding, how much friction force is there? There we go. And so, but obviously there is a breaking point. Now, okay, I'm sorry, I missed, did you raise your hand a little bit earlier?
Oh, I was just gonna say what she said.
Okay, okay. So, static friction is always going to match until you hit that breaking point. So that's why the formula for it, there's a less than or equal to symbol in it. So static friction is less than or equal to whatever that breaking point is. Now, in terms of that breaking point, it's been found that if I've got 2 surfaces, so let's say these are the 2 surfaces right here. I don't want to slide them across each other. If they're pressed really tightly into each other, it's a lot harder to get them to move apart. So how tightly they're pushing into each other is some factor in how much friction there is. Well, how tightly they're pressed into each other, basically normal forces are indications there. So it has something to do with normal force. It also has something to do with the surfaces themselves. It's a lot easier to push this on this surface than it would be on the carpet, I'm assuming. So the other factor deals with the surfaces. This is known as the coefficient of, with the S there, static friction.
What's that symbol called?
That's a mu, mu. I think we deal with mu again in 151. In 251, I've got a video on don't confuse these mu's, where mu actually represents 5 different things. Because, again, we have only 100 letters that we can work with, counting uppercase, lowercase. At some point, we have to reuse. But sometimes when I want to represent a situation as frictionless, I'll just write mu equals 0 as the shorthand. All right, questions up to here?
That's not a Y, is it?
That's the symbol I use for normal force.
Okay.
Oh. So I'll go into a little bit more detail on that after I answer Lisa's question. All right, so that breaking point is this mu s times y, whatever this coefficient is times the normal force, how tightly these two things are being pushed together, or really, how much force is required to keep one from going through the other. Once it starts moving under this model, once it starts moving, it's relatively easy to keep moving. And so the kinetic friction, cleverly labeled F sub k, is equal to mu k times the normal force. And anyone want to take a huge guess at what mu sub k represents?
The coefficient of kinetic friction.
Absolutely. So if you wanted to look up the coefficient of friction and you found a table of it, you would go into whatever your search engine is, hopefully not Bing, and just type in coefficient of friction, you'll come up with a table, and it'll give you two surfaces and then a number. Sometimes it'll give you two numbers. Well, actually, most of them will give you two numbers. They'll give you a mu sub s, and they'll give you a mu sub k. So in this model, if this is my friction force here, and this is my applied force, in other words, the force I'm pushing against something, the applied force increases, the friction force increases, and they will match each other until I hit that breaking point. So Fs max, which equals mu sy. Once you reach that breaking point, the friction will drop off. And that's supposed to be a straight line, or a horizontal line, slightly better. And the friction is the kinetic friction. All right, so that's the generic. This is the way friction is handled in most textbooks, but not all. Now, there are some textbooks which I've seen it more and more. There's some textbooks where they'll say, all right, this is the way you deal with it. Then they'll have the 251 textbook we were using before the current one. They had a page on a different model and basically said, all right, this is another way of looking at it. However, we're going to use the classic formula of this. There is a group at NC State trying to come up with something better. This formula was, I think 1790s is when this formula was developed, and it hasn't really changed since. There's a group who study tribology. I guess the study of study? No, they do tribology. It's the study of basically friction or things rubbing against each other. Trying to come up with a more sophisticated model. However, for the most part, friction is not a physics issue, it's an engineering issue. It's an everyday issue. But for instance, on my dissertation, and actually my thesis, there was no friction involved at all. So, and engineers are practical people, so they have something that works, and so that's why generally it hasn't developed much since the past couple hundred years. However, there is another group which is basically saying this value of mu sub k and mu sub s, large error bars. They might tell you that the coefficient of friction is 0.3, but really it could be anywhere from say 0.2 to 0.4. And you really, there have not been really any precise experiments to narrow it down better than the illusion, or better than these vague fuzzy numbers. And what they say is there really is no difference between static and kinetic friction, other than the fact static friction will match until you hit the breaking point, and then you just have friction. And in that model, the friction will match until you hit the breaking point, and then this is just some value of mu times the normal force, where the coefficient, it's the coefficient of friction, not static or kinetic.
So what's the difference between the two graphs as far as the force being applied and the breaking point? Like why do you need more force on the first graph, and then it drops, the force applied drops?
I think the difference in the model is, I sort of view this as, in the video I call it the nook and cranny model, that I've got kind of like interlocking pieces here, and I might have them jammed together, but I'm trying to basically push this against another piece. And so once you get it out of the grooves, it's a lot easier to move. So that's sort of this model. This model is more of an attraction model, that in this model, it's not, like a puzzle piece where one piece is pushing against another one. It's the fact that when you press surfaces together, there's a much bigger attraction between the two surfaces at the atomic level, and that's what it's fighting against, is that attraction. Now, it seems like it'd be very clear which model works. I mean, these are very two distinctive graphs, one where the friction drops off and one where it doesn't. And I tried to find some document, some article where they've actually done the high precision experiments. All I found was a college senior thesis where he went into it, and there was such huge error bars. I mean, he was not willing to run 1,000 experiments with the exact same thing over and over again. So, I guess it's an area at some point someone will do.
People you said NC State?
Say again?
You said people at NC State are trying to find that model?
That's possible. The people at NC State, when I saw the talk they gave a couple years ago, they were looking more from a theoretical. They were trying to work with theoretical foundations and build out, as opposed to the purely experimental approach.
When you say the breaking point, is that the same thing as saying what it takes to move that object? I just want to make sure.
Yes,
Okay.
yes.
I just wanted to make sure that was right.
That critical force that's required to get it to actually start to accelerate.
Okay. Thank you.
All right, so that's sort of the underpinning of it. I haven't really gotten into a calculation. Now, Musa, was your question more around the actual using numbers, or the more of the theoretical aspect?
That's the theoretical aspect.
Okay, so this answers your question. Okay. All right. Other questions? I'm about to erase this and talk about forces in general. Find out who's watched the videos. I don't believe I've talked about FTOM directly. All right, FTOM, what does it mean?
Other.
I'm gonna gravitational. Did I do gravity in the video?
It's gravity. Yeah, I would say gravity.
These are the type forces that we will be dealing with up until, well, for, at least for most of the course. The symbol used, friction, I got what I call the Baruch F, a little bit of a curl there, a little bit of flare. Tension, I don't use capital T, I use F sub T, just to save hassle later on when I use capital T for something else. Normal force, I use a Y, because, well, again, the trivia of the videos, why do I use the letter Y?
Because it's force, I mean, so it's,
That is,
I haven't watched the videos.
Does it have to do with being perpendicular to surfaces of contact?
I would think a capital T would work better if we're dealing perpendicular.
Why do you use that much?
There's one of them, and,
That's all now.
oh. My high school physics textbook used the letter Y, that's fine. And gravitational, there's two types, as was mentioned, there's weight and there's the force due to gravity. Weight is a specific case of the force due to gravity. Force due to gravity, I generally use F sub G when I'm talking about the generalized gravitational force, such as I'm dealing with incredibly tiny things like the force between you and the book in front of you or the desk in front of you. Or I'm dealing in outer space and I'm dealing with the force of gravity between planets, or moon and planet. Weight is when I've got a planet or huge planet, moon, something along that, sun, star, something along that scale, and a smaller object right near the surface. A small object would be pretty much anything on the surface of the Earth. Yeah, so elephant would be counted as small. Oh, and other, it's problem specific. Because forces come in pairs, so whenever I'm doing a force diagram, I'm always going to put down two of them, with the exception of other. Not saying that there's not another part of that pair, it's just another part I don't care about. For example, when I had the example of the pushing 1 Newton against a box, I didn't really state what the source of that 1 Newton force was. And it didn't matter. So that's an example where I would just draw one force, that 1 Newton. But there was another one pushing back against something. All right. I don't want to repeat that which half of you know, or maybe I do need to repeat what half of you know. We'll just zip through this potentially quickly. What's the requirement for friction to exist? Okay, and
Desire relative function.
assuming this table is level, if this were frictionless, this object would not move. if the table were perfectly level. And so it doesn't have any desired relative motion, so therefore at this point, sitting right here, if I added friction to the table, it doesn't change anything. So there's no friction acting on this. However, if I tilt the table, if it were frictionless, that would start to slide, so therefore there is desired motion, therefore there is friction acting on it. So that's the desired part, relative to what it's touching. I have a pin on this calendar. As I started to move, if this were frictionless, what would the pin have done if I start to move? Yeah. So there's desired relative motion, desired motion relative to what it's touching, not relative to the earth, but relative to what it's touching. So it would go that way, and friction hates that. So which way would friction act on the pin? Yeah. It opposes that desired relative motion. And since we said it, let's go ahead, let's see, and then direction with respect to objects. Opposing desired relative motion. Tension, what's the requirement for tension?
Taut rope or chain, eccentric.
What about the requirement for other?
Unknown or irrelevant source.
What?
Unknown or irrelevant source.
Okay. I feel like I misspelled this every single time. Is that ENT or ANT?
I think it's ET.
You were saying E also? Or you just?
I have E.
I have E.
I'm also the best.
It's an A or an E.